much. Thanks everybody for being here. Thanks to the organizers for inviting me. It's been really fun so far.
Especially after yesterday.
Yeah, especially, yeah. So, good. So, one of the themes, I guess, of this workshop is, kind of so-called exotic dynamical regimes. And, something that we've already heard about and will kind of continue to hear about is that sometimes quantum systems remember their initial conditions and they don't thermalize, or maybe they thermalize slowly. So one example of this is quantum antibody scars. These are some nice review articles on the topic. And just so we're all on the same page, this is a phenomenon that was observed experimentally. And essentially what happens is you prepare some initial state and then evolve it with some Hamiltonian, and then what you can see in these pictures where white is sort of your qubit is in the 1 state and black is your qubit is in the 0 state, is that you see these long-lived, it's an experiment, so it's a very short time scale, but surprisingly coherent oscillations. And if you actually dig a little bit into what's going on, it's lots of observables oscillate because the state, when you evolve it up to time t, is kind of periodically returning to itself. So actually what's happening is that the overlap with the initial state is sort of oscillating, and you can define, this is data from another model, but this is plotting that overlap. And what you see is that there's this kind of family of initial states where they're kind of periodically returning to themselves after some amount of time. So the system is kind of undergoing some kind of periodic orbit, if you will, in Hilbert space. And this periodic trajectory is unstable. One way that you can see that is if you look at the blue line here, that's some other initial state, and that the overlap decays really fast. So you can change the initial state, and then these revivals go away. You can also perturb the model. So like in this picture, what happens is, the red curve is one of these reviving initial states. And then the blue is basically you change the Hamiltonian a little bit, you perturb the model, and then the revivals start to go away, right? So it's unstable in the sense that you can kind of change things a little bit or a lot, and then this phenomenon goes away. Now, there's an interesting connection that's been made to unstable periodic orbits in classical dynamical systems, because it turns out that lots and lots of sort of chaotic dynamical systems still have some regular, regions of regular phase space, and one of the things that you can have is orbits. So here, it's fun to look at pictures. So this is a particular classical dynamical system called the kicked top, which is a nice example because it allows you to kind of, there's a well-defined classical limit, but it also can be studied quantum mechanically. This is not actually a model that I'm going to be studying. I'm just using it for the nice picture. But it's basically dynamics on the sphere. So you have a vector that lives on the surface of a sphere, and then according to some rules, it just gets kicked around. So it processes for a bit, and then it gets kicked. And what you see here, this picture, is basically Poincare section. So it's like each dot here is kind of you're taking a snapshot after some amount of time of where on the sphere the system is, so this kind of reveals to you the structure of the phase space just by following an ensemble of initial states. And what this picture kind of tells you is, like, if you initialize yourself in this region that looks kind of like static on an old TV, if anyone has experienced that. If you start yourself off here, like the way that you should look at this picture is, you'll explore most of the sphere, because basically, you start here, later on you'll be here, later on you'll be here, okay? But then if you start yourself over here, what actually happens is that you undergo a closed trajectory on the sphere. And if you can really pinpoint yourself here, this is like a fixed point of the map that doesn't update. So these, sort of regular regions kind of form around fixed points of the map. And these are also kind of, unstable in the sense that, you can change the initial state, or you can change the model parameters, right? And, and that'll make the dynamics chaotic, right? So as an example, if you pick this orbit here, it's an unstable orbit in the sense that, if I kick my initial state a little bit off of this orbit, I'm in the chaotic region, and then I have no hope of returning. Or if I change the model, I change the kick strength, for example, I can shrink this island of stability, and then what for one value of parameters would be on a regular orbit, for another becomes a chaotic initial state. So there's a natural question, and we're not by any means the first people to ask this. It's been studied a lot. Is whether there's a systematic way to stabilize these unstable orbits, both in the classical setting or maybe in the quantum setting, which is something that I'm going to talk about today. And what do I mean by stabilize? Well, one thing that would be nice is if you could turn them into global attractors, which would be in the sense that you could initialize the system anywhere, and then eventually you would fall onto this orbit because it's kind of the steady state of some dynamics. Okay, and if oh yes. Yeah. Yeah, that's right. So, and dissipation. Yeah. Exactly. Absolute, like, that's the whole talk. Okay. Thank you. Okay. You want to give the? No, okay. Okay, good. Yeah, so, okay, does global attractors kind of, sound like it's too good to be true? Well, it's not necessarily too good to be true, and actually it's been demonstrated in the classical chaos literature that you can kind of convert some of these unstable orbits to attractors. So some people in the 90s figured this out. They did it for a few classically chaotic maps. They did not do it for the kick top, but I'm going to use the kick top picture anyway. But the idea of their approach is, it's called stochastic or probabilistic control of chaos, and basically what you do is you randomly intervene in the chaotic dynamics to apply a control operation. So just to give you an idea of what this looks like, or how that works, I'll bring the kick top back. And let's say that I want to stabilize this orbit that I've highlighted in red. Okay, how would I do that? So let's say that I initialize myself somewhere in the chaotic region. Then I have a protocol, which is a discrete time protocol, where at each time step, I flip a biased coin, and if the coin lands, say, heads, I apply the chaotic map. Okay, so let's say that my coin lands heads a few times, right? I bounce around a little bit. But then eventually the coin will land tails, and if the coin lands tails, so with probability P, I apply a control map, and what does that entail? Okay, so the first thing that you do is measure where you are in phase space. This is trivial for a classical system, but for a quantum system, it's non-trivial. So I wanted to highlight that. Like the measurement aspect is not really, that's like step 0. Step -1. I mean, it's not even something that you think about. And then you figure out which point on the orbit is closest, right? So you do some, calculation to do this, maybe, if you like. And then you apply feedback that kind of pushes you towards that point. And, how much you push is kind of up to you. You could pick the system up and just put it right on the orbit, but that's kind of cheating, I would say. But you could give it just a little push, like a little modest push, and it's still in the chaotic phase space, but it just got a little bit closer to the orbit.
Understand that then you want to apply everything to another context. But in this context, what's the use of it? Once you know what is the distance and so on, why not cheating, as you said?
Well, I think the idea is that you would kind of like this process to just kind of like, run in the background and not perturb the dynamics necessarily too much. But it's also interesting from the compute.
The part that you need to compute is a bit... yes. The computing part is a little bit
because once you do the computation, you say, okay, I go. You know, I understand that probably then in the quantum context is more, but
yeah, it's more like, you know, in different, depending on like, you know, where you are. I mean, you could always push to the same point on the orbit if you want. I mean, you could control onto a fixed point, and then there's no, that's not relevant, you know. I mean, but yeah, yeah, right. Okay, so something that's interesting and that was shown in this work and a few other works for a few models is that as a function of this parameter p, which is the rate at which you apply this control operation, you can get a phase transition, and that phase transition it's like a bona fide phase transition with you know, with critical exponents and everything, and you know, it's a transition where the unstable orbit becomes an attractor. So there's an uncontrolled phase where the dynamics remains sort of ergodic to the extent that it can be. And then there's a controlled phase where if you wait long enough, eventually you hit the orbit. Yeah. Okay, so now what we would like to do is to kind of generalize this in two ways. One way is we want to apply it to quantum systems. And then, you know, the kick top and actually, you know, all of the maps that I'm aware of to which this specific stochastic approach was applied, you know, are single body examples. So there's one top, it's not a bunch of coupled tops. So we want to generalize this along these two axes. And one way that you can do that is, you know, in a quantum circuit, you can imagine having a quantum circuit, and then in between your gates, you can do some measurement and feedback, right? So the measurement now has a non-trivial action on your quantum state. And one of the things that measurement does is that it can affect the entanglement structure of the state. So this kind of brings this question into contact with this subject of measurement-induced entanglement phase transitions, where you can have a transition between, say, an area law phase and a volume law phase as you reduce the rate at which you're measuring the system. So this is one kind of interesting feature that can happen in the quantum context and in the many-body context, because entanglement is also a many-body thing. Okay, so so it's a legitimate question, how does unitary feedback alter these measurement-induced phase transitions? And there's been some work on this by us and by others. Okay, so how am I going to do this? And like, you know, I guess is somebody keeping track of time? I don't know exactly how much. Yeah, okay, good. I'll just keep talking, and you can all leave when you get tired of it. Okay, good. Yeah, so what I'm going to do today is tell a story about an example where we define a many-body model that has a particular classical limit. It's not like a standard kind of large S, you know, large spin classical limit. It's a discrete limit. It's a cellular automaton limit, if you like. I'll talk about what that is. And then we'll demonstrate that in this model, which is kind of set up to directly like mirror the classical protocol that I just described, we'll demonstrate the existence of a control transition in the classical and quantum examples, because the classical is already interesting because it's many-body, which is different from what was previously done. And also, phase transitions are hard in quantum systems to study numerically. So if you have a classical model, that's a lot better for you, right? It can anchor your understanding. And something that's already interesting here that has to do with the generalization to many-body is that actually the nature of this phase transition is kind of long range for reasons that will become clear. And I'll talk about what long range means in this context, but that's kind of an interesting tidbit. And then, you know, the other thing with the quantum is that there's this entanglement transition, and it's a legitimate question, like when does the entanglement transition happen? When does the control transition happen? Do they happen separately? Do they happen at the same time? Right? So there's actually a non-trivial interplay between the two transitions in this model, which is kind of interesting. Okay. Any questions before I start? Okay, good. So, okay, so this is really like meant to mimic the classical setup. So what I have here is at each time step, I'm choosing randomly whether to apply a quote-unquote chaotic operation or a quote-unquote control operation. My chaotic operation is essentially some quantum circuit. I apply this circuit with probability 1 minus p. And this is a scrambler that has a notion of an unstable periodic orbit that I'm going to talk about. It's kind of a simpler version of scarring. It's not as rich as all of the stuff that happens with scars, but it's kind of proto-scarring. And then with probability p, I apply this control operation. And the control operation has two parts. There's a funny measurement that I'm going to talk about, which is actually a collective measurement. I'll talk about what that means, but think like your qubits are in a cavity and you measure the photon, that kind of measurement. And this initial part is determining the closest state on the orbit. So this is kind of the compute. I measure some information, and then I don't measure the whole state of the quantum system, because that would be not what I want. But I gather some collective information that doesn't fully disentangle the system. And from that, I can figure out what's the closest state on the orbit. And then, I talked about how there's like a parameter in this control, which is how hard I push, how much I push to the orbit. And there's actually an analog of that in this model, which is there's a probability Q to do a local correction. So once I have figured out which state on the orbit I want to push to, I can go and, on some fraction Q of the sites, I can do some extra measurements, and then conditioned on all of these measurements, I can apply a corrective unitary that makes the system locally look more like one of the states on the orbit, okay? So it's some kind of, again, it's not quantum error correction, but it's kind of, it's like classical error correction, essentially. Right, so that's what this second part is. So there's some phase diagram as a function of those two parameters, and that was actually, I'll come back to it, but I showed it in my summary. Okay, so what's the chaotic circuit? It's a little bit involved, but it's inspired by Rydberg atom quantum simulators, because eventually it would be cool for somebody to do this, ideally. So it has kind of two stages. The first stage is you're basically doing Rydberg blockaded X rotation by an angle pi over 2. And this is actually like, up to some phases, it's basically a Toffoli gate, if you are a classical circuit fan. And what does this do? Basically, you flip the spin if the neighbors are both 0. Otherwise, you don't do anything, okay? Yeah. And this part is classical, essentially, because it's not, if you put in a bit string, you're going to get out a bit string. And it also turns out to be integrable, which is not what we want either. So then there's this extra piece that we do to kind of break integrability, and it's basically a sort of XX type coupling that's projected such that it satisfies the Rydberg blockade. So what this does is particle hops if the outer neighbors are both 0, but then it's blocked from hopping if one of the neighbors is 1, okay? But this guy has an angle associated with it, so I can tune this angle. So what that means is that, now there's a cosine and a sine, okay? So what happens here is that essentially means that, like, quantumly, there's a probability to not hop, and there's a probability to hop, right? And, if I want to, I can set this angle to whatever pi over 2, and then this becomes a bit string update. So my classical limit is just setting this theta to pi over 2. And then this whole thing becomes a classical circuit. And then I can kind of, if I wanted to, we didn't do that in this work, but if I wanted to, I could perturb away, and set theta to pi over 2 plus epsilon or something. And just, it's like this theta is like h bar in some sense. Or like 1, I don't know, 1 over h bar, whatever. Okay, good. So why do I do this stupid thing? I mean, this is like, I just spent like 5 minutes explaining some dumb circuit to you. Why? So the reason that we chose this specific circuit, other than that it would be nice if somebody did it, right, is that this circuit happens to have an unstable periodic orbit. And this is actually a feature that is common to like a whole class of cellular automata. It's actually generic for a cellular automaton with a translation invariant update rule to have an orbit whose length is order 1, okay? So this particular orbit is 3 states, and basically the system cycles between everybody 0 and then the 2 alternating nail states. And you just cycle through these 3 states. And the thing that's nice about the way that this is set up is that for any, these gates that I chose happen to annihilate, like the generator of these rotations annihilates all the states on the orbit, so it actually doesn't do anything. So even when I make the model quantum, there's one set of initial states that will do this, even if a different initial state is going to get entangled. So I can show you pictures starting from one flipped spin in both cases. So if theta is pi over 2, you just get some like bit string dynamics that you can easily follow classically. But then in the quantum case, what happens is you flip, and then you get this kind of thermalization, so to speak, and then this like sort of blue-green wash is basically all of your qubits kind of averaging, your magnetization averaging to 0, essentially. You could make a picture like this if you averaged a bunch of realizations of this over the random. These gates are randomly positioned. The angle is chosen, but the where you put the gates is random. Okay, good. And we have an order parameter. I said that this is a phase transition, so it has an order parameter, which is essentially this operator that counts the number of domain walls, but they're kind of sublattice domain walls. So basically, this thing is 0 when the sort of next nearest neighbor sites are aligned together, okay? So the excitations in this system are sort of next nearest neighbor domain walls, and your control protocol, your correction protocol, which I'm going to talk about next, is trying to get rid of this, okay? Okay, so how does the control circuit work? A little bit more detail. So what are you doing here? So what this is doing is measuring the magnetization on the even sublattice and the odd sublattice separately, okay? Now, why do I want to do that? It turns out that if you know that information about a bit string, you can compute by taking some plus or minus the sum of these things, you can compute the Hamming distance to the 3 states on the orbit. And the Hamming distance is basically just the number of bits you have to flip to get to one of those states. So the closest state is the one with the smallest Hamming distance. But then quantum mechanically, you can also measure this thing and then ask which of these things is smallest, okay? And then that's some quantum analog of the Hamming distance. So this is telling me how far away I am from the states on the orbit. And these are intrinsically many-body because I'm only measuring the magnetization. I'm not actually going and measuring each qubit. That would be too much. And I'll talk about how you could do that with a cavity in a little bit. And then the local correction step is just looking for these domain walls. So you do some measurements that kind of tell you if there's a domain wall or not. And then if there's a domain wall, you get some more information, you do another measurement, and then you, based on that information, you can decide, since I know which state on the orbit I'm correcting towards, I don't have to annihilate the domain walls in pairs, right? I know if I'm going to the all 0 state or the 1, 0, 1, 0, So using that information, I can locally get rid of domain walls because I can say, oh, I want this state to look more like the all 0 state. So if one of the spins is 1, I'll just flip it to 0. Good. Okay, and as I said before, P and Q, which is, P is the rate with which you apply this control operation, and Q is how many sites where you go and check if there's a domain wall or not. And those are my 2 parameters, okay? And some example trajectories, because pictures are cool. This is an example starting from one flipped spin, but now I'm not just applying the chaotic map. I'm also doing this control. And what you see is that if, I'm only applying my control 20% of the time, an initial bit flip propagates, and then eventually this kind of orbit gets washed out, right? So this is the chaotic phase, so to speak. Then there's this thing, which looks like some hidden message, but I promise it's not. This is p equals 0.5, and you get these kind of percolating strands, right? So if you've studied like directed percolation or one of these classical models, this looks maybe like it's undergoing a phase transition, and you would be correct in thinking that. And then this is in the controlled phase. Basically, my bit flip just gets caught eventually, and actually any initial state with a random configuration of bits would actually fall onto this eventually. And then kind of the jitter here, but like here I stay on the 0 state for a long time, is just because I'm still, after I hit the orbit, I'm still doing the chaotic map sometimes, and the chaotic map updates you, but then I'm also doing the control. So this is like I did the control operation a bunch of times in a row. My coin landed whatever I said, heads or tails, a bunch of times. And then when the chaotic map gets applied, you update to the next state. Okay. Any questions about this? Is essentially the story without anything quantitative. So good time to pause if there's any questions. Okay, now you can fall asleep. Okay, no, not yet. I want to tell you how do I measure this? How do I measure the magnetization of a collection of spins? I was talking about this with Dan Stamper-Kern, who has Rydbergs in cavities, and I was like telling him this, like it was like, such a cool thing, and he was like, yeah, I know. But it was cool to me. I just learned it. I'm always excited when I learn something new. Okay, so how do you do it? All right, let's say you have a bunch of spins in a cavity, okay, and you want to just measure the magnetization of them without measuring the individual spins. Okay, how do I do that? Well, if your spins are dispersively coupled to the cavity, what that means is that the dispersive coupling chi is basically you couple to the cavity mode via the magnetization. So if you measure the cavity frequency, it gets shifted by an amount that's chi times the magnetization. So by looking at the cavity, you are indirectly measuring only the magnetization of the spins without looking at individual spins. Okay? And this does a projective measurement of the magnetization. Now, this is a really interesting type of measurement, this kind of collective measurement, because for one, it accommodates volume law entanglement. So if you start in a volume law state and then you measure the magnetization, the most likely outcome is 0 magnetization, and there's exponentially many states in the 0 magnetization sector, so you can still have a volume law state after your measurement, okay? So that's one thing, is that it takes out entanglement, but it doesn't take out all of the entanglement. And actually with high probability, a volume law state remains volume law. And it can even create entanglement, because if you put the system if you do a Hadamard transform on your qubits, and then you measure the magnetization, the outcome is a Dicke state, okay? And that's basically an equal weight sum over all of the states with that magnetization. And that state is useful, for example, for quantum sensing, and it has logarithmic entanglement entropy. So log n entanglement for n qubits. So you can even create entanglement. So it's interesting to be like, okay, well, how's that going to affect the entanglement transition, right? Okay, now you can go to sleep. Okay, so all right, classical limit. So this is just on the the classical model on bit strings, and what we're computing here is the realization averaged order parameter. So I'm averaging over random initial product states, which remain product states because it's the classical limit, and random instances of the circuit. Because this is all numeric, yeah, all numerics. It would be cool to do some analytics, but this is kind of a first step. And you see here we did like system sizes 300 to 540. You could go bigger if you wanted, but we also did 16 to 32. And the reason is, when we do the quantum, we're not going to be able to go to big systems. So it's going to be helpful to us to understand how bad the finite size corrections are. And you can see from looking at this, right? This, the blue, looks like a nice second order phase transition from a textbook. And then this guy, it looks like there's a crossing there, right? So if you looked at this picture, you'd say, oh, the scaling dimension of the order parameter at the transition is 0. But there's an exponent that's non-zero. And you only see that when you go to big enough systems. So if we were studying the quantum, and we did the silly thing of actually initially studying the quantum model, and then we were seeing all kinds of stuff that doesn't make any sense. It's because, we were looking at small systems, right? So that's useful to us. We can do scaling collapse on the big systems, and we find that kind of as I advertised, the transition is around 0.5. There's a correlation length exponent 2.3, roughly. I mean, this is all kind of numerics, so we have error bars. And then there's a non-zero scaling dimension of the order parameter at the fixed point, or at the transition. And what's cool is then we can say, okay, what kind of finite size corrections do we have to add to our data? The quantum data is only going to be able to get here, so we're going to have to add some finite size corrections to scaling. What should they be? How big are they going to be, right? So we can do that here. So see this inset, the red and the blue points are all collapsed, right? And we do this by adding some extra parameters to our fit.
But so when you will do the data collapse for the quantum data, you consider beta, nu, MPC fixed with these values, and then you will play with A and alpha?
So
or?
that's how we did this calculation.
Right.
So we took these as kind of the ground
And
truth.
when you will go to the other, you take this
free.
value. No, they are all free.
Yeah.
Ah, okay.
And then we ask, how close are they? Because
Okay.
the nice thing is that when you get your parameters out from your fit, like this A, for example, you can see how big is A. And then, A, L to the minus alpha. You can put in A, you can put in L, put in alpha. You can get a quantitative sense of how bad your finite size effects are, right? Okay, and we also looked at some dynamics, did some collapse there. Oh, yeah.
What is alpha?
Alpha, what number? Yeah. For this, I don't remember. It's in the paper, but I don't remember. I mean, so what we did was, because you don't have control over how bad your finite size effects are, but you have control over how hard you search the parameter space, right? So we always kind of converged our collapses, kind of, just to make sure that we were always getting, because for example, so here we got a nice guess for the for what the exponents are, but you can if you're doing the collapse for another parameter or something, then you can say, okay, are my finite size effects here, according to this fit, worse than they were in the classical, or are they about the same size? And if they're substantially worse, that means that probably I could have jiggled some bits in my computer and gotten a different answer, And
just my question was about those are the subleading terms, right?
Yeah, exactly.
So
yeah.
the larger alpha is, the less relevant.
Exactly.
They
Yeah.
are, right?
A and alpha.
So
yeah.
My question was whether alpha was like 1, 2, or 0.5.
Yeah, I don't want to say because
Okay.
I'm going to say the wrong thing with
I look at the
probability
paper.
1. But it's in the paper.
Okay.
I promise. We can look at it together if you want. Okay. So then I also looked at the dynamics. How am I doing on time? Perfect. This is what I like. This is good. So we also did some dynamics to get the dynamical critical exponent of the transition called Z. And we got Z as 0.8, and that should ring alarm bells for you. You should be confused about that a little bit. I'll talk about why later, why you should be confused, and then I'll hopefully resolve the confusion. But basically, Z less than 1, TLDR, Z less than 1 means long range, essentially. There's theorems that prohibit Z less than 1 in short range interacting systems. Yeah, sure.
So on the left panel, you consider T scaling with L with the
Yep.
exponent which is very close to Z. Is it on purpose or?
Yeah. So we want to try to do get our data at a time that's sort of not too long, not too short. Because if you wait too long, there's a higher probability that you can just end up on the orbit even, by accident. I mean, basically, you have to make sure that you're observing at the right time. And like, so people usually look at t equals L, but that's because Z is usually 1 for these like measurement-induced phase transitions. So we had to do some kind of self-consistency. Actually, I did the numerics for this paper, so if they're bad, it's because I did it. So I was doing a self-consistency loop, basically, because, you know, because, you know, you can assume a different Z and then try to collapse everything, you know. Yeah. So, yeah, we did a kind of variational sort of thing. Yeah, good. Cool. All right. Great. So that's classical. And now quantum, we only have the small system. And I mean, look at this data. I mean, look. This is averaged over 10,000 realizations, and it still looks like this. So just to tell you, you know. We do our collapse. We get exponents. The transition moves a little bit. Nu is the same as the classical to within our resolution. Beta gets bigger by a factor of 2, and that seems actually pretty robust, and we don't understand exactly why the scaling dimension of the order parameter is bigger. There might be some way of understanding that, but we haven't dug into it much more. We also got Z, and we get Z of about 0.8, 0.9, all consistent with the classical. Okay. And Z is still less than 1. So why? Okay. So as I said, it's forbidden for strictly local interactions, but if you have long-range interactions, Z can be less than 1. And just to give you some sense of like what Z means, if you haven't studied phase transitions too much, is it tells you about how correlations in space develop as a function of time. So Z is kind of the relationship between, so there's a correlation sort of time, if you like, and a correlation length, and they're related by this exponent Z. So you can think of this, this tells you something about critical slowing down and all of this stuff. And basically, if Z is 1, that means that your correlations are kind of spreading linearly in time. You have a light cone. And then, if Z is greater than 1, for example, Z equals 2, that's diffusion, right? So you get, then, but then you're going in, your sort of cone of propagation is, your information propagates slower, right? But then what happens when Z is greater than 1 is you're outside this linear light cone, and your information is traveling, faster than light, if you want to be provocative, which I don't really want to. But yeah, so, but this is not unprecedented. It's known to happen, for example, in the Ising model with power law interactions. And what happens is basically, as your power law gets bigger, 1 over R, right? We had a nice talk about this. But you revert to short-range behavior when alpha is big enough. But then what happens is that the critical exponents run as a function of alpha as you make alpha smaller and go closer to like all to all. So the thing that's interesting here, to me anyway, is that everything in our protocol is strictly local, except in the control part, you did that magnetization measurement. So basically, the only thing that could explain this is that when you do this magnetization measurement, you're producing correlations, right? Because I do a correction operation over here, I do a correction operation over here, but they share information about the magnetization measurement. So these become correlated operations, okay? And that is why, it's the only reason why you could get Z less than 1. Okay, we also looked at the entanglement transition. Oh yeah, sure. Yeah, I can go back.
Yeah, exactly. Before you go, if you look at the pictures at the beginning, the ones you said that they do not contain a message.
Yeah, right.
It seems that everything is actually happening within the light cone there.
Yeah, so there what's happening is that you're getting, so what you would have to do is basically average those pictures.
Okay.
Over
So if
distances,
you average,
and then you would
do you
see a light cone. You would see a light cone, and the shape would be dictated by the Z.
But would you see that Z is less than 1 in those pictures? Because
I mean, I haven't tried that exact calculation, but I think you should, yeah. but maybe, yeah. No, but I see your point. But the other thing is Z depends on your parameter also, on your parameters. So you could look more short range or more long range depending on where you are in the phase diagram. That's the other thing. So you can get short range behavior in the model. And I'll show the phase diagram later.
Okay.
Yeah. Sorry?
I guess it depends on this probability Q to correct, right? Because if that's
Exactly.
very small, then everything has to be local, right?
Exactly.
But if
And
that probability is high, then you do a lot of stuff based on
Exactly.
a single measurement.
Yep, that's exactly what we'll show. I have a plot of this. Yeah, and there's the correlation length exponent is also changing.
Yeah.
And it's the same thing. It's the exact same thing. Yeah, good. That's great. Great questions. This is great. Okay, so we also look at the entanglement transition. And we looked at multiple entanglement measures, but the one that's kind of the easiest to analyze and that has the least finite size effects is this ancilla purification thing. So what you do is you take an extra qubit and you entangle it with your system. And then you scramble the system only. And because you started off with some entanglement, it gets spread around. And now your entanglement is kind of delocalized over the whole system. And then you start looking at it and doing measurements. And eventually, your measurements will learn enough information about the system that the state of the extra qubit collapses. And that's where this entanglement transition happens. It's basically when the measurements learn enough information to disentangle the extra qubit. And you can think of that there, as like also, once my measurements are learning enough information about the system to disentangle the extra qubit, that's also when I can control, probably, right? That kind of is intuitive. And indeed, the entanglement transition usually precedes the control. They can occur at the same time, and I'll talk about that later. But what we do is basically this reference qubit disentangles as a function of time, and you get Z from that, and it's consistent. The Z is consistent with our with the order parameter transition. Okay. So it seems like that's really how fast the dynamics are happening. And then we can get location of the transition, and we can get the correlation length exponent, and these to within, we have pretty big error bars, so, we can't really say that the transitions are separate. Okay, so how do these transitions kind of interplay? It has something to do with the density of local corrections, Q. So this is basically the phase diagram. So essentially, as a function of Q, you see that basically the bigger your Q is, the smaller P you can get away with to control because you're correcting more, right? If Q is 1, then you're going to control in like order 1 time steps, and all you have to do is like apply the control operation once, and then you're there. So that's why the shape is what it is, right? And then the red dots here are the estimate of the transition point from the entanglement. And I think the dots are actually purple, but up here they look blue, so I'll call them blue dots, are the order parameter. And you see our very big error bars for which I take full responsibility. Okay, but what's interesting is basically you see that they're kind of within error bars of each other. This Q is 0.2 is kind of the cut that we looked at the other plots for. But you can change it and you see that there's this shape. But then as Q gets smaller, it looks like they actually do become, we can say that they are actually distinct as Q gets smaller, which is kind of interesting. And I'll come back to that. But then you see that Z, as Q increases, Z goes down. So it becomes more long range, which is exactly the discussion from before. And the more long range it gets, there's also a corresponding, I apologize for the double axis, but the red here is the correlation length exponent. That also gets bigger. So the model becomes more long range, the correlation length exponent gets bigger as well. And then again, this is from the entanglement data and the order parameter data, and they seem to be kind of tracking each other, except, you know, when Q is small, right? Here we also, it seems like the new critical exponent is different. So it seems like the transitions are actually splitting off from each other as Q gets smaller, okay? Now, why, right? Sorry, I didn't mean to yell. Why are they so close? Okay. So there's a heuristic argument for this, which is essentially, you know, at the control transition, you reach the target state in a time order L to the Z. And the control, the like orbit, is a bunch of product states. So the system has to disentangle either before it gets controlled, or, you know, it can't disentangle faster. I mean, it can't disentangle slower than the control, because by the time you hit the control, you're going to be disentangled, right? So let's suppose that if you were just doing this protocol with measurements and you did no feedback, there's some measurement-induced phase transition for this. So let's say for, like, as a straw man thing, let's say Z is of order 1, it's just 1, right? What that means is, like, you know, if the control has Z less than 1, then the control is going to happen faster than the measurements would be disentangled. The measurements alone would be disentangling. So that means that the entanglement transition kind of has to piggyback off of the control transition. And another way of thinking about it is that it's not the measurements alone that are driving the entanglement transition. It's also the feedback that you're doing is disentangling the state as well. And that's why the control and the entanglement seem to have the same, you know, the same Z. Now, okay, so now the question is, when does Z become greater than 1, right? Once Z is greater than 1, this is kind of allowed again for them to be separate. The system will disentangle faster than you control it, right? And if you look here, I keep going to point this thing, but anyway, so oops, sorry. So this line, horizontal line, is where Z is 1, right? And where does that happen? It's, you know, Q a little less than 0.2, right? So Z goes above 1 somewhere here, and then I look, and then the transitions are splitting, right? So it's when the control transition starts reverting to some short range limit that we see the transitions separate, okay? So we thought that that was an interesting thing. So let me summarize. So we defined some quantum many-body version of this stochastic control protocol. It involves collective measurements, which you kind of need because you need to figure out where to push. Yeah, and those collective measurements kind of give rise to this long-range transition, which is kind of interesting. And that long-range nature gets imprinted on the entanglement dynamics as well, which is kind of also interesting. I mean, yeah, it's always interesting when the entanglement and control transitions kind of happen together, at least, because generically they do not. Generically, the entanglement transition comes before. So, you know, Outlook, what can we do? So we're actually working with IBM to see this experimentally. We have better data now, but this data already looks pretty good. I mean, this is experimental data, no error mitigation. No error, not even readout error mitigation. Like, it's really like, it's like, I mean, yeah. So, and we get we get agreement for the critical exponents. We didn't do this model because it's a little, you know, it's a little out there, but we did a different model, and it has a control transition. We didn't observe the entanglement transition, but these measurement-induced entanglement transitions are very, very hard. Some would say impossible to observe experimentally. But we get quantitatively accurate critical exponents, which is cool. That paper is coming eventually, soon. Then you can also say things like, so, you know, like Dario was talking about dissipation, right? So you can think about if you average over all of the measurement outcomes and the circuits and everything, basically what you're doing by doing this interacting with the system, the measuring and the feedback, is you're making a quantum channel, right? You're designing by interacting with the system, you're making it experience a quantum channel. And quantum channels also describe noisy dynamics. So you can say, what if I added noise as a perturbation to this, right? The experiment does that on its own without us asking to. Sometimes we ask it not to, but we didn't even ask it not to here. We didn't even error mitigate here, you know? So that tells you something about like actually interacting with your system and doing measurements and designing a quantum channel can kind of make it a little bit more robust to noise, which is interesting. And that's something we want to explore. Then you can also be like, well, you know, so again, I told this story to Dan Stamper-Kern, and he was like, isn't there an easier way to make a product state? And I was like, yes. So it would be cool to target cool quantum states with this protocol, you know, GHZ states, Dickey states, AKLT states, and some of these have been done already. You know, for kind of frustration-free states, you know, you can imagine like, okay, I'm just going to measure the Hamiltonian terms and do some, you know, it's not hard to imagine all the things you could do with this, but there's other cases that are, you know, not all models are frustration-free, and then it's kind of interesting. And then, you know, yeah, maybe with these sort of dynamic or adaptive circuits, like, you know, for example, like maybe you could try to stabilize state that's useful for sensing, for example. Like Dickey states are useful for sensing, GHZ states are useful for sensing. Maybe, you know, the robustness to noise also feeds into applications in some way. So that's something that we're also interested in. Yeah, so with that, thank you for your attention and nice questions. Yeah.
Other questions? Okay, people want to go to lunch.
Not Zlatko.
Zlatko is not interested in lunch.
So have you thought about what's going to happen with the Hamiltonian PXP limit?
No, I think that's kind of interesting. Like, then it's like, okay, I want to try to target maybe the scar state, scar manifold or something. I guess you know,
because there we have this semi-classical manifold,
right?
And I guess you could also do the full quantum, which is already non-ergodic, right? So
yeah.
You don't need to do any extra stuff.
Yeah, that's true. Yeah, no, we haven't thought about the Hamiltonian limit. That might be interesting to explore. Yeah, yeah. Like I said, I don't want to make a guess because I'll probably just give the wrong guess.
But do you think that even studying the classical system could be interesting there?
It could be, yeah. I mean, you know, it's maybe tricky to like figure out where in phase space you are. Like, I mean, at the classical thing, you just look, right?
Yeah.
But you know, if you wanted to kind of port some of that over to the quantum by maybe measuring the overlap with one of these, you know, the Husimi function, if you will, on this phase space, you know, which is, you know, expensive. It's a lot of measurements to do that, but you know, I think for me that would be like kind of the first question I would want to figure out: what kind of measurement do I need to do? Tomography is probably not what you really want to do.
Just one quick more.
Oh yeah.
So when they put these Rydbergs in a cavity, they can't do these tweezer arrays, right?
Dan Stamper-Kern has tweezers in cavities.
So they can.
Yeah.
And they can put them in the blockade regime.
Yeah, I think that's the plan. That's the plan, I think. Yeah, or maybe they already did it. They definitely did this way of like making a Dickey state by measuring. That was like, again, that was like I was so excited when I learned about this, and then it's known. I mean, in the quantum optics community. Yeah, right. The super radiance. Yeah, that's right.
Some more? Okay, let's
Great.
thank
Thanks,
Thomas.
everybody.